I want to talk about a model class I developed over the years with co-authors, the so-called endemic-epidemic model framework. And we considered recently an extension of that, where we include discrete-time serial interval distributions. So this is what I want to talk about. This is a joint work with a former PhD student of mine, Johannes Bracher, who is now in Karlsruhe. And the focus really is on prediction, on forecasting, infectious disease forecasting. But I will also talk a little bit about how we apply this forecast, this model framework to COVID-19, to data here from Zurich. And I will talk about this at the end of this presentation. So, by the way, this is the main building of the university, which is very pretty, as you can see. And unfortunately, currently it's not so populated, as you see on the picture. But actually, we had a lot of easing here. Schools are reopening in Switzerland. So the pandemic seems to be kind of over in Switzerland, at least. We just have a few sporadic cases, and then hopefully there will be no second wave. Yes, okay, so forecasting epidemics. There was an interesting statement from WHO 6 years ago, in particular in the light of the current pandemic, where they had a publication here entitled Anticipating Epidemics. Epidemics are contemporary health catastrophes. And you see part of the article here on the left. And just to quote from that article, on the right, there is this citation here: forecasting disease outbreaks is still in its infancy. However, unlike weather forecasting, where progress in recent years has been substantial. So that's perhaps, one of the key messages, that forecasting, and more specifically probabilistic forecasting, is a well-established tool in many other areas of science, weather forecasting, yeah, meteorology, climatology, but also economics. But at least 6 years ago, it was still in its infancy, and things have changed a lot since those 6 years, but still I think there is more to do, and I will point a little bit to what can be done. So there have been recent forecasting challenges and projects in the context of infectious diseases, and here you see a few of them. So you see for various bugs, dengue, Ebola, influenza, there have been actually challenges where different forecasting teams have tried to come up with the best prediction, and one forecasting team was obviously the winner. And more recently, there was this COVID-19 forecast hub, which you see the link here. And this is something I want to show you on a website. So if you click on that link, you actually end up here. So this is an exciting initiative by Nick Reich and co-authors, who aim to forecast COVID-19 incidence and also cumulative death in the US and also in selected states. So for example, here you see the forecast for the cumulative death in New York. Let's go back to incident death. So you see the peak here around mid-April. And you see different forecasts. You can move, the forecasts here visually. You can pick other states, you might be interested. For example, well, California. And so it's a wonderful page you might be interested to play with. It produces a week ahead forecast, and the interesting thing is it actually produces a number of forecasts, not just one, but different tools are applied, which are shown in different colors here. And then based on those different forecasts from different methods, actually a so-called ensemble forecast is created, which kind of averages in a clever way across all these forecasts and comes up with a eventually better forecast. So that's something I don't have time to talk about ensemble forecast, but that's a tool which is also very useful in weather forecasting and which seems also quite promising in forecasting infectious diseases. So let's put this away here again. Okay. One interesting feature about all these challenges and projects is that they all focus on univariate time series. So in a sense, they all look at a simple example like this one. This is dengue fever in San Juan, Puerto Rico. That was part of one of the challenges. And so this is kind of what the data looks like and the different research groups obtained. So you see the number of reported cases over the years, and left from this red line, that's the training period. So that was the period, the data that the research teams obtained. And then the research teams have been asked to predict what's shown here on the right, on the test data, and to predict several aspects of that. So you might predict the whole epidemic curve, or you might predict the incidence at a particular day. You can produce 1 week ahead or K week ahead forecasts. So you might want to predict the peak time. When does the epidemic peak? And so on and so forth. I will come back to this. Yes, and a few years ago, out of this lab by Nick Reich, an interesting paper came out, infectious disease prediction with kernel conditional density estimation. So that's short KCDE. And so they proposed a new method which turned out to produce pretty good forecast predictions, probabilistic forecasts of disease incidence of infectious diseases. Okay, and as it happens, I got interested in that paper because it was actually using a framework I've developed over the years, this endemic-epidemic model framework as a competitor. And so I want to talk a little bit now about this EE model framework. That's really nearly 20 years old now, so I'm a bit embarrassed about this. It's, you know, the first paper came out, I think, in 2005. Well, okay, 15 years, but we've extended it in various directions. And as you can see here, there have been more recent papers, 2014 and 17, and also more recently with Johannes. So what's this about? So in a sense, what this framework proposes is a decomposition, an additive decomposition of disease incidence into an endemic part and an epidemic part. So the endemic part, in a sense, captures everything that you are not able to explain by infection, by an infectious process. So it covers seasonality, may cover differences in population size, differences in socio-demography, and so on and so forth. You can include covariates, maybe temperature or humidity and other things. Whereas the epidemic part, that really is kind of the infectious bit here, that describes the incidence of this part of the incidence as a function of previously infected individuals. And so this is inspired by mathematical models for infectious diseases. And it turns out it can actually be derived from a discrete time SIR model that was mentioned at this conference a lot, with serial interval fixed to 1 observation period. So John Wakefield from Seattle has looked into this in more detail, and you'll find the argument in his 2 papers here. The nice thing I think about this model framework is it's all based on likelihood inference. So and it's all nicely implemented. So it's pretty fast. You can fit, you know, sequentially models. You can fit a lot of models, and it would just be a matter of seconds. You don't have to deal with MCMC or, you know, convergence problems and so on and so forth. So it's very nicely implemented, and it's really nice. I'll come back to this at the end of this talk. Okay, so the univariate model formulation for dengue that was used in this paper by Ray and Nick Reich and others was a very simple formulation, univariate, where you say, well, the number of cases I have in a particular week is negative binomial with some mean lambda t and some overdispersion psi, and the mean has this decomposition into mu t and phi t. I hear some noises, so can you please all switch off your microphones, please? Thank you. Okay, and nu t is this endemic part. So this is what we model with sine cosine forms to capture seasonality, weekly seasonality with period 52. Whereas the red part is a very simple form of this autoregressive epidemic part, where we regress the incidence on the number of cases in the previous week, right? And so you can see, oh, well, this is pretty simple. It just has a few parameters, really, and you can easily fit this with the maximum likelihood. And that formulation has been compared to this much more complex KCDE approach in Ray et al. And no surprise, KCDE was actually better in the performance. And so we thought about, well, what could be maybe the main reason why KCDE is actually doing much better in prediction than our EEE or EE model framework. And one feature that is different in KCDE from the originally proposed EEE model is that it has higher order lags. It not just takes into account the incidence in the previous week, but it takes into account also the incidence in further weeks before. So what we then try to do is to include higher order lags in this model framework. So the formulation is now slightly extended. So this epidemic part is now an autoregression on the number of cases in the previous week and in week t-2 and in week t-3 up to t-p. So p is the order really of this autoregression. And the other new thing is that we then need to introduce weights, or more specifically normalized weights, which sum up to 1, and which describe the decay of the importance of the coefficients of these YTDs. And this can be actually thought of in an infectious disease sense as the serial interval distribution. So that's, in infectious disease, that's the time between the appearance of symptoms in successive generations. So we really want to estimate that serial interval distribution to get some knowledge also about this this epidemic characteristic. And so the question is, well, how do we estimate these weights? And of course, the simplest version is just to do some unrestricted estimation, so that all of them are positive or non-negative and sum up to 1. This is the last option mentioned here. You can imagine if p is large, this will easily get unstable, and ML estimates might not converge. And so we also considered a bunch of other options, a shifted Poisson distribution. So just shift the Poisson distribution by 1 to the support 1, 2, and so forth, up to p, and normalize it. So then there is one parameter to be estimated, this kappa, a triangular distribution, which captures a linear decay in the weights, a geometric distribution, which captures a geometric decay. So those are the versions we looked at in this paper with Johannes, where you have the link here to the preprint. Yes, so how does that work? So we reanalyzed Dengue on the same partition of test and training. So this is first the results on the training data. So what you see on the left is the improvement in AIC of models with order 2, 3, 4, 5, 6, 7, compared to the model with lag 1 of order 1. And you see already a massive improvement of 70 units for order 2, and more improvement even for higher order. It's no surprise that the blue line, this is the unrestricted model, is best. But the geometric, as you can see, this is the yellow one, also performs pretty good and seems to have kind of an optimal order around 5 or 6. And it seems to perform better than the triangular and the Poisson weight distribution. In the middle plot, you see the estimated weights out of this formulation. And so the red one is just the first order one, so that could have been really omitted. So that obviously has weight 1. And then Poisson triangular geometric. Geometric is the yellow one, which drops in a geometric fashion. Unrestricted is non-monotone. It goes, down and up, as you can see, the blue one. And we also compared this to well, estimates of the serial interval distribution from the literature. And that was in this paper by Sirai et al. 2017, which had a peak actually of the weights in week 3. So you see that's actually quite distinct, quite different from what we estimated based on this data from San Juan. The right plot gives the autocorrelation function, and you see actually this literature estimate gives doesn't really remove correlation, so there's a strong autocorrelation of 0.5 first order. And also the first order EE model has strong autocorrelations, whereas the geometric one, the yellow one, actually has autocorrelations which are close to 0, which look reasonable from a statistical perspective. Okay, so that was just fitting. And now when it comes to forecasting, we have to think a little bit about first, well, how do we actually forecast? And I said, I want to do probabilistic forecasting. And then the question is, how do we evaluate the forecasts? So just to make some advertisements here. So I've written a paper here with Sebastian and Johannes about probabilistic forecasting in infectious disease epidemiology a few years ago. And we also written a chapter in this handbook of infectious diseases on forecasting based on surveillance data. That just, by the way, appeared this year. I'm not sure if it's already on the shelf of Rob. Maybe it should, maybe it shouldn't. Anyway, so what do we do to assess the forecast? Well, first of all is how can we calculate probabilistic forecasts in this EE model? Well, because of the formulation, it turns out one step ahead forecasts, well, they are just simply negative binomial, if you ignore the parameter uncertainty. And so that they are very easy to compute. It's just kind of a trivial, really, computation. K-step ahead forecasts, predictions, can also be generated easily through Monte Carlo simulation, notably not Markov chain Monte Carlo. All you need to do is go sequentially through time, and you can do this by a Monte Carlo simulation, and you can actually then compute a proper score, the so-called logarithmic score, efficiently using a trick which is also known from MCMC simulation called Rao-Black equalization. So details can be found in the paper. So this is how we generate the forecast and how we also evaluate the forecast. We use this logarithmic score. When it comes to forecasting, it's always important to have reference forecasts, because you may have a wonderful model, which seems to describe everything very nicely and fits very well, but however, which may produce awful forecasts. So it's important to have simple models as reference models and to see if you are actually doing any better than a naive, simple model. And so the reference models we use here are of two kinds. So the first kind is a naive seasonal model, which basically just looks at the incidence in the past years in a given calendar week, and then takes the average and basically this is my mean prediction for the future calendar week, and adds uncertainty according to a negative binomial distribution. There's a bit more fancy approach, which also includes autoregressions, the so-called GLARMA model framework, which is implemented in our package. That's also what we used here with these sine cosine terms. Right, so here you see for a part of of the dengue data, the dengue test data really, the 1 week ahead predictions on the left. And in the top, you see the predictions based on the first order model. And at the bottom, you see the predictions based on the geometric weight serial interval distribution. And you see, they actually don't differ much, but the geometric forecasts seem to be a bit more smoother. And that makes sense because they take into account more historical data, so they ought to be smoother. So just to emphasize this, so those are not fitted values, so those are really 1 week ahead predictions. So for example, if you look at a particular time, this will be the 1 week ahead forecast given the data up to the previous week. Okay, so one way to evaluate how well calibrated such forecasts are PIT histograms, which are shown here on the right, and they are shown only for the geometric forecasts. So basically, PIT stands for probability integral transform. So basically, it looks at the probability integral evaluated at the observed value. And if your probabilistic forecast is well calibrated, then these PIT histograms should be close to uniform. And so you see the 1 week ahead forecasts of the geometric decay model are actually close to uniform, so they look pretty good. However, the 4 week forecast, so when you try to predict further into the future, they have a problem here in the upper part, which indicates that there are more observed cases in the upper tail of the predictive distribution than actually there should be. So there is some miscalibration here of the 4 week predictions, it seems. Right, and now if you want to really compare the average predictive performance across all the weeks where you apply, where you compute 1 step ahead forecasts, we computed this average log score. And so let's look first at the left figure. So the smaller the better. So the worst model is the black line here, which is this naive reference model, and all the models we considered are doing much better than this. And the x-axis is actually the forecast horizon, so 1 week ahead, 2 week ahead, and so on and so forth. And that makes also sense. So the further you predict into the future, the less accurate your predictions really are. It's a bit difficult to disentangle all the different lines here in the left plot. So the right plot gives us a better indication of what's happening. So the right plot looks at the difference in mean logarithmic score against KCDE, so our competitor. So that means the straight line here is KCDE. And if we are below that, then actually the method is actually performing better than KCDE. If we are above it, the method is performing worse. So you see that actually the EE models with higher order lags, for example, the geometric one, perform slightly better than KCDE when it comes to 1 or 2 week ahead forecasts. If you predict longer into the future, then actually things turn and KCDE is better than geometric. The literature one doesn't perform so well. This is the orange one here. And also the first order autoregression, that's the one that was used in the paper by Ray and others. That's also always worse. But it's interesting to see that this simple modification of the EE framework with higher order lags, actually gives us better predictions, seems to give us better predictions for short-term forecasts than this much more computer-intensive KCDE approach. Of course, such a statement should be, validated also on other data sets and so on and so forth. But still, it's an interesting finding of our work here. Just to mention the two reference models, GLARMA, naive. We saw naive was already very poor. GLARMA performs a bit better. This is the gray line here, and it's also better at week 1, but no longer at week 2, right? So it has not a bad performance, slightly worse than the E models here for horizons 1, 2, 3, 4, and slightly better for horizons 6, 7, 8. Right. So that was what I wanted to say about forecasting univariate time series. And I guess, as you all know, surveillance data on infectious diseases rarely comes as a univariate time series. It usually comes as a multivariate time series. So it may look like this here. So here we look at an example of viral gastrointestinal disease incidence in Berlin, Germany. And we look at norovirus on the left and rotavirus on the right. Again, weekly number of reported cases. And so this is a multivariate time series of dimension 12 because we have 12 districts in Berlin. And things might easily get more complicated. You might have even data stratified also by age group, which is actually the case here for the data here from Berlin. But I don't have time to talk about this here. So, but I want to emphasize the data we obtain from registries is often, well, is usually stratified by region and by age group and maybe even by other factors, for example, gender. And so it would be nice to develop, tools to really perform multivariate predictions. And the EE framework is actually able to do this, as I will show you now. So here you see the incidence in selected districts, so Pankow, Spandau, norovirus, and rotavirus. So you see the usual patterns in surveillance data with seasonality, higher incidence in the winter, occasional outbreaks like here for rotavirus, and so on and so forth. So how can we extend the EE framework to spatio-temporal data, really? So, and can we combine it with these higher order lags, with these serial interval distributions? And the answer is yes. So the formulation now looks like this, and the important bit is now the epidemic component. So UD is still my serial interval distribution, but new are now weights, WJI, which describe the spatio-temporal spread of the disease, really. And so again, we have an endemic component with seasonal terms. Phi IT is the epidemic component. This is the serial interval distribution. And the weights are now chosen in a very simple manner with a power law for spatial transmission. So basically, the closer two regions are, the more transmission will there between the two regions. Okay, so that's something we looked at in work with Sebastian, and that performed pretty well to capture spatio-temporal transmission. Although, of course, it's quite simplistic, and I'll tell you in a minute that it actually can be combined with something pretty clever, which is a gravity model. So a gravity model, that's a proposal that comes from the group of Brian Grenfell, and I think we had a talk about from his group, I think 2 days ago, actually. And he was talking about the gravity model, Bjornstad. And so the idea is, of the gravity model is that, if you are infected and if you are moving to a different region, then you are more likely to move to a region which is densely populated and infect somebody there than you are to move to a sparsely populated region where basically nobody lives, because you don't want to go there where there are no people. So you will tend to go to other big cities, for example, even if they have the same distance as a small town in rural areas, right? So that's the idea of the gravity model. And that's nicely integrated in this framework by taking population size into account and adding population size as a covariate in the epidemic component. And it's recommended to do this on the log scale. So log EI is included here. So we considered two models, one with the gravity model and one which is less parsimonious, a full model, which just is kind of a saturated model, which has phi IT district-specific intercepts in this formulation phi IT. You see that gets quickly complicated. I don't want to stress these details too much. Please look at the paper if you want to know the details. Again, we have two reference models, a naive seasonal model with indicators now for calendar week and district, so kind of a multivariate formulation with kind of just indicators for week and district, and also this negative binomial GLAMA model applied separately to the 12 time series. So how does this work? So improvements in AIC on the training data, and you see here norovirus, rotavirus, gravity model, full model, and you see again a massive improvement in terms of AIC compared to the first order model. So first order gravity is the reference, 0 and all values are negative, so all models really fit better than this reference model. And as it turns out, again, the geometric one is actually the best. And in terms of AIC, it's always the full model with the geometric decay, which performs best. And here's the estimated weight distribution. Geometric is again in yellow color. So you see how the geometric decay goes down. You can compare it to the unrestricted, the blue one, which actually looks very similar for norovirus and also for rotavirus. So actually, for both of these diseases, the estimated lag distribution looks pretty similar. You also get estimates of the seasonal behavior. There was also a Christmas indicator in the model because the incidence of these diseases is typically lower during Christmas because people stay at home or don't go to the doctor. And you see this quite nicely here in these plots of the endemic component, both for norovirus and rotavirus. And here you see the estimates from the different models. The power law estimate, that was this parameter that describes spatial dispersal. So that's also estimated from the data. Yeah, that should be emphasized, as well as the overdispersion parameter from the negative binomial model. Okay, and then we do the same again, separate the data into training and test, and now look how well does it actually predict on the test data. And so as you can see, so what you see here now are mean log scores of univariate one step ahead predictions. And again, the reference is the first order gravity model. And you see all numbers are negative here. So that means all these models perform better in terms of log score. And the best is again the geometric. What's interesting is that for norovirus, it's actually the full model which performs best. For rotavirus, it actually turns out that it's actually the slightly simpler gravity model, which actually slightly performs better than the full model. But the difference is not really large. A side note, a relieving side note, is that the reference models, naive and GLAMA, actually they perform worse than the first order model, right? So we are in a good situation where our models and our model extensions really perform better than these reference models. Okay, you may also be interested in case step ahead predictions, and now it gets really interesting because the one step ahead predictions in this model class are still conditionally independent, but the case step ahead predictions are not. Right, so once you go ahead 2 weeks or 3 weeks, because of the dependencies between time series, there is dependence between these predictions. So what you want to apply is really a multivariate score to evaluate the quality of the probabilistic forecast. And so we use this multivariate log score to quantify this. And so you see here the mean multivariate log score of multivariate case step ahead predictions of the different models compared to the naive model. And so the left is for norovirus, and you see, well, all do better than the naive model, and the best is the geometric one, the full model, geometric, and the second best is geometric with the gravity model. And it's similar for rotavirus, but actually the order changes. So now the best model is actually the one with the gravity model here, the dashed one here at the bottom. So I think encouraging results that this multivariate extension predicts better than the reference model. Okay, I'll give some discussion now, and then I give this outlook to COVID. So discussion of this work so far. So the incorporation of serial interval distributions into the EE framework gives improved model fit and improved predictive performance. I just looked at predicting the number of cases in the next week or week ahead. You can, as I said at the beginning, also forecast other targets, and that's what actually people do. So you might be interested to forecast the whole epidemic curve over a season. You might be interested in specific features such as peak timing, peak incidence, and onset timing. And I should say that some of these features are actually the forecast targets in these challenges from WHO and other agencies. So they might, for example, ask you to predict the peak timing or the peak incidence at peak timing. And that makes things more complicated. We can also predict this with the EE framework, but I haven't shown you this here. I think the key feature of this approach is that you can predict multivariate time series, and you can really incorporate the multivariate structure in your forecasts and the spatial temporal structure in the examples we've been looking at. Of course, there are also a few minus, and so one thing refers to, well, the resolution of the data, and all the data I showed you so far was given on a weekly resolution, which is a bit coarse, and so if your infection dynamics actually act on a finer resolution, maybe just 1 or 2 days, then obviously, aggregating it to weekly counts and then analyzing this with the HHH4 framework with the EE model seems maybe not as the best thing you should do. And what will happen actually, it will increase over dispersion in this framework. So if infection dynamics actually happen within a single week, then this will be captured by increased over dispersion. That's basically all you can do if the data has been aggregated to a coarser level. The other comment I want to make is that you may also have underreporting. That's something Johannes has looked at in a comment he wrote last year, and there's also joint work coming up on this. And you actually quite often have underreporting in all these surveillance data, and even for COVID-19 you have underreporting in the case of asymptomatic cases. So what happens if you just observe, let's say, half of the cases really, and it turns out that this may also induce kind of an artifact in the serial interval distribution. It might actually induce a geometric serial interval distribution. So that's quite an interesting aspect, that underreporting is kind of, may induce artifacts in the estimates of the serial interval distribution. Yes, so to come to my outlook, I want to now show you a little bit about how it looks like with COVID-19 in the canton of Zurich. It happens that I have been analyzing these data on a daily basis, really, over the last month, and computed predictions of the number of hospitalizations and also the number of ventilations in the canton, because that was, of crucial importance, obviously, for the health authorities. And the input variable was basically the number of new infected cases reported, which you see here. So the black dots, those are the observed number of cases over the last month. And as you can see, There was a peak in March, but then it went quickly down, and we now really at very low incidence in May. And one thing to note is this is now daily data, so that's in a sense much better, right? So we have daily data, not weekly data. That's an achievement. And the other thing to note is that what you see here is actually the fit of an EE model, of an endemic-epidemic model, which seems to fit the observed one quite well. And so I want to show you briefly, how this model was selected. And one covariate that was included in this analysis was a covariate for social distancing interventions. Also here in Switzerland, of course, there was a lockdown and everything closed and school closed and shops closed and so on and so forth. And that was kind of, in the second half of March. So I included this indicator, which was 0, and then quickly jumps to 1. And then maybe a month later, easing has started, and there were steps 1 and 2 and 3 of easing. First, some shops open, and then some schools opened, and now we are in a state where all schools are open again. And so I tried to mimic that with this functional form here for the social distancing intervention, and so that just went in as a covariate in the epidemic component, really. And so this is the output you get when you fit such an EE model. So that's the output of HHH4. This is what the function is called in the package surveillance. And so it really looks like, like the output of a GLM, let's say. So you get an estimate and a standard error for all the parameters in your model. So I have an intercept for the autoregressive component. This is the covariate for the social indicator that I just mentioned, which has a negative effect on the epidemic component. This is how it should be, right? So it shows that the lockdown measures have been successful, and it's also highly significant if you compare it to the standard error. There were also weekend effects here, both in the endemic and in the epidemic component. AR is the epidemic component, autoregressive, End is the endemic component, and this is what calls these kind of holes here every 7 days. So this is important because reporting on weekends is different from weekdays. Usually less cases are reported on weekends. And then finally, what kind of lag distribution has been used in this analysis? And because the data is daily, it's really important to use a lag distribution. So you see the lag weights actually have this form here, 0.17, 0.3, 0.27, 0.16, and then they go down again. And so visualized, they look like this. So actually here, it turns out that this Poisson model fitted better than the geometric. And in particular, the Poisson model now is non-monotone and peaks at 2 to 3 days for the serial interval distribution. So I think these results are encouraging. We just starting to apply HHH4 models, EE models to COVID-19, but it seems to work quite nice, actually, quite well. One thing we want to look at in a project is also to look at the data age stratified. So because, as you know, it's a big discussion about, for example, whether children infect adults or in the other direction. And so we want to use contact data, which is available from contact surveys. And we want to include this into the EE model framework. And actually, Sebastian has implemented this model extension already a few years ago. And that's also available in the software. And so a contact matrix looks like this. So here you see the contacts a participant of a particular age had with members of the population of his or of other age groups. So for example, if you are a participant of the age around 14, then you tend to talk to 14-year-old, but you might also talk, to 24-year-old or to 44. year old. So this data can be incorporated, and this is something we want to do to investigate in more detail what the effect of the different lockdown measures really are. And this will be done in this project, Suspend impact of social distancing policies and underreporting of the spatio-temporal spread of COVID-19. And I'm glad to report that just got funding, but from the Swiss National Science Foundation, and also, you know, I have excellent project partners on board, including Neil Hens, who talked about contact data already 2 days ago at this meeting, and also other experts. So this is what we want to look at. We just started really on June 1st. So, but this is our project, and we hope to get to grips with the EE framework to look at the spread of COVID-19 in more detail. Okay, last slide on software. So the package surveillance in R, I guess many of you know this, has a function HHH4 where the basic endemic-epidemic model is implemented, and that's described well in this paper in the Journal of Statistical Software, which, so you can follow running examples in that paper and kind of repeat the analysis with the code, but just copy and paste the code from that paper. And the extension to discrete time serial interval distributions, and that I talked about here in this talk, that's available in another package called HHH4 add-on, available at this link on GitHub. So I think I'm finished now, and I thank you for listening, and I look forward to questions. I just show a few references at the end, which may be useful to some of you. Thank you.